Welcome back for day 1 of Unit 8, Part 2. In this portion, we're just going to be trying a practice problem with our new equation that we just learned about pendulums, which is that the period of a pendulum, t, is equal to 2 pi square root of L over g. We're going to try a practice problem using this equation, and the practice problem that we're going to be trying today comes from page 379 of your textbook. Yes, it is one of your homework problems. Take a look at page 379, number 4A. I have my textbook here. You have your textbook in front of you. The question says, calculate the period and frequency of a 3.500 meter long pendulum at the following locations. And part A, which we're going to try together, is at the North Pole, where the acceleration due to gravity is 9.832 meters per second squared. Hey, did you notice that the acceleration due to gravity changes around the Earth? Well, that's because the Earth actually isn't a nice perfect circle. The Earth is really kind of shaped a little bit more like this, with edges that are a little bit fatter around the center. Obviously, this is an exaggerated drawing, but what that means is, up at the top, you're much closer to the center of the Earth, versus far out here on the equator, you're much further from the center of the Earth. So G actually changes depending on where you're standing. We say 9.81 all the time, but 9.81 is an average for the average radius of the Earth. So anyway, fun things to consider. Doop, 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 doop. Let's try this problem. To start, we're going to start by listing our knowns and unknowns. It says that the length of this pendulum is equal to 3.500 meters. That's the length of the pendulum. We're looking for the period of the pendulum and the frequency of the pendulum if G equals 9.832 meters per second squared at the North Pole. Okay, let's go ahead and give it a go. We know that T is equal to 2 pi times the square root of L over G. We have all of those things, so finding T is easy. We don't need to rearrange it all. We can just plug in numbers here. T equals 2 pi times the square root of, my length is 3.500 meters. And G here is 9.832 meters per second squared. Plug that into my calculator, and you get a final answer. Go ahead and try it now while I pick up the pencil I just dropped on the floor. Okay, we're back. Did you try it? If you did, you should have gotten 3.749 seconds. Like so. But wait, that's only half the problem. Notice, the problem also asks for frequency. I didn't give you an equation for frequency in class, but could you find it? Sure, here's what you would have to do. Isn't period the amount of time per oscillation? And isn't frequency oscillations per time? Do you see how those two concepts are just flip-flops of each other? They're just reciprocals. So if I wanted to find the frequency is just 1 over the period. Likewise, bonus fact, the period is 1 over the frequency. Same, yes? So to do this problem, I'm going to start with this equation that says that frequency is 1 over the period. What I'll do after that is I'm going to plug in my equation for the period. But I'm going to plug it in all upside down. So I get that the frequency is equal to 1 over 2 pi times the square root of not L over G, but G over L. Now, there's a little division for my work. Now I can plug in numbers and get to a final answer. 1 over 2 pi times the square root of 9.832 meters per second squared divided by 3.500 meters. Oop. Plug that into your calculator and you should get 0.2664 hertz. Or, if you don't like hertz, can't you also use units of 1 over second? And that totally works as well. So there you go. That's how to try one of those problems. Hope that was a helpful video for you for a little bit of a practice problem. And I'll see you all next time. Have a wonderful, wonderful, wonderful rest of your day.